For this third part of taking you a tour and simulating this op-amp, I'm going to show you how to ask some questions. What happens when I turn the knob bias current? If I increase the bias current, what happens? Well, if you've been doing your hand calculations on the small signal model of an op-amp, you already know, but it's kind of mathematical. And for me at least, it helps if I can do the math and then also understand, kind of get the pictures in my head by letting the computer draw the pictures for me. That's my way. Preference, I guess. All right, so how do we do that? Well, we're going to keep our simulation here. Let's go from 0.01 hertz to a gigahertz. That's fine. We're going to leave our DC simulation, so we're going to still do an AC simulation. And then what we're going to do is, now that we have these parameters, I'm going to step my parameters. Okay, so I right-clicked on here. I'm going to activate this by turning it into a dot command. And I'm going to step by decades, which is a factor of 10, a parameter. That parameter is I bias. You'll notice that I called this one I bias with the capital I, but my parameter itself is a lowercase I. This is kind of bad form. LTspice is going to change the parameter, not the value of I bias the current source. I actually got caught with this, hung up for a few minutes. I'm like, why isn't my current source going? Because I was doing a parametric sweep instead of a device sweep or steps. And so on. So I'm going to help myself out by making this a lowercase I and match. It always is a parameter, but now at least visually I get I bias, and it's this one. Okay, so I'm going to step it in decades. I'm going to go from 1 or 10 micro, the number, but this is for a current source. This is microamps, to 10 milliamps. And I'm going to do 1 step per decade. So if it's 1 step per decade and I start at 10 micro, I'm going to do 10 micro, 100 micro, 1 milli, and 10 milli. You can count how many steps that is in your head. Okay, I'm not going to do that because I'm talking out loud. That's it. Now let's run the simulation and see what we get. Run this, and I get a family of curves. Isn't that cool? So it says V out and it shows green color, but really all 4 of these curves, remember, it's 10 micro, 100 micro, 1 milli, and 10 milliamps. That is 1, 2, 3, 4. Okay, that's why we get 4 curves. We see our phase plots here as well. Should I include phase? I want it to come back. All right, so we'll do that. Let's keep the phase here. What we want to do is, like, we can say, all right, well, select the steps. If we do a bunch of steps, we can select these. So we have I bias. This is this. This is 10 milli, 1 milli. This is a tenth of a milli, which is 100 micro. And then 1 times 10 to the minus 5 is 10 micro. And these are my steps. Okay, auto range, sometimes it's useful to keep that off. But we're going to look and we're going to see we go from, I'm going to put a cursor on. Okay, so I'm going to put a cursor on here, and you notice that this is on here. I'm going to put this right at 100 kilohertz just for fun. This is 10 microamps. How do we know it's 10 microamps? Because it's the same result that we had before in the previous video. Of course it is. Okay, so we have, what do we have here? I got notifications, just kicked me off in my head. How do you know what step this plot returns to or corresponds to? Well, just right click on your cursor. Right click, it says cursor 1, I bias is 10 micro, 1 run, 1 out of 4. Alright, so it's a right click is how I got that. How do I put my cursor up here? I can't click on it. I can't click on it. It's really annoying. You use your arrow keys. Alright, so use your arrow keys. Arrow. I hit the up arrow. Here we are. We're right at 100 kilohertz. I can step that over with my arrow keys. 100 kilohertz, and if I right click on this, I get my information. It's 100 microamps. What I'm actually interested in is how does my frequency response change? You notice that when I went up by a factor of 10, okay, I'm going to put this at a megahertz. So before we were at 100 kilohertz, I increased my bias current by a factor of 10. My unity gain frequency also increased by a factor of 10. If you're following the math, then that's totally not surprising. GM over C over CC is our rough estimate of what the current is, what the unity gain frequency is, and how it maps back to our two-stage operational amplifier. Go over here, we see that there's stuff that happens down here. We get our second pole and our first zero show in. You can see this curve kicks up a little bit. That's a zero coming into play, and it comes back down again. Then we have a second pole that is near that frequency. Okay, important for us is that our phase response at the unity gain frequency, which is way up here, which is 127, it doesn't hit 180 degrees or minus 180 degrees. Put this under feedback, we'll be stable. Once we hit 180 degrees, a negative 180 degrees or positive, put this op-amp in like a feedback thing, like we do with the normal op-amp. We have just made an oscillator. It's going to oscillate at that frequency, and that's a bad idea. Unless you're trying to make an oscillator, and then you start to understand where the phrase amplifiers do and oscillators don't, where that phrase comes from. It's an expression of frustration when you're trying to make an amplifier and oscillator. They always do what you don't want, especially in the real world. All right, so that was how we stepped the current here, and that was way easier. In my opinion, that's way easier than like right-clicking on this and changing this to be like 10 micro, and then you run the simulation and do all your commands, and then 100 micro, and then 1 milli and 10 milli. Okay, I like the dot step. Well, if you're in my course, you know that I also asked you to step CC in 3 different steps. So 360 pico, and then a decade down to 36 pico, and then up to 3.6 nano farads. How do we do that? Did you know that you can do a 2-dimensional step and it is awesome? Well, I knew that because I read the manual. Well, if you want to read the manual, let's read the manual together. Okay, so LTspice. Go down here. I like to use arrow keys because it's just way faster. And I'm lazy and I like to go fast. Okay, lazy not in terms of I don't want to work, but lazy in terms of I don't want lots of labor to get my results. Okay, I care about my results, but I don't. All right, so dot step. Here's an example. Okay, here we can do a list of things, which is cool if you just want to list out the things, you don't want to think about it. Here we're stepping a model parameter, and that's wonderful. Okay, the first order, first step is sorted. Okay. You know what? This doesn't tell us much about stepping. I'll tell you what. I'm going to do a little experiment, and I'm going to say, what if I did step, param, start, stop, number. It doesn't show up in here. All right, how about this? Dec, param. What was the parameter? CC. I'm going to go from 36 pico to 3.6 nano, and I'm going to go 1 per decade, and I say OK. And what do we get? Do we get an error? No, we don't get an error. What just happened? I'm going to zoom in here. On here, I did a 2-dimensional sweep. I did one was a decade sweep of my I bias, and then I added a thing on the end here. It wasn't in the documentation. But it is a common thing that happens that's available. another decade sweep of a parameter called CC from 36 pico to 3.6 nano in one step per decade. Well, here's what we can do. We got a whole bunch of these. If we look at our steps, we can see what we have. Oh, look at this. iBias was 10 nano at 36 pico, and look at this. 360 pico, 360 nano. This is all 12 combinations. This is pretty cool. This is really cool, actually. All right, now our plots start to get pretty nasty. What I kind of want to do is I want to make some measurements on here, but it gets old doing measurements with just cursors and doing cursors over here. Look at this. It looks like there's two next to each other. That's really weird. That is interesting, isn't it? So I'm going to go over here. I really want these two, the purple and the pink, I guess. Oh, there's one. So that one is 100 micro and 3.6 nano. Okay. And there's my second one, which is 10 micro and 360 pico. Do you notice that my bias current went down by a factor of 10 and my CC went down by a factor of 10? If they both went down by a factor of 10, we're going to get on the same plot. That's why we have double up, double up, double up, double up, double up. And then this one is the extremes. That's why they double up here. Isn't that cool? You know what? Our math predicts that. Our math predicts that. So when we're doing our small signal analysis and we look at it, you know, we shouldn't be surprised. It's still cool to see. All right, but it's not magic. What I want to do is I want to measure what my unity gain frequency is for every single one of these points. I could do this manually and step my cursors. I gave you some tips on how to do that. I would really like to measure it. Do you see what these are? Dot measure statements? Oh yeah. Here's one of them. Oh man, don't do that. This dialog box is not helpful to me. Dot measure statements are kind of like a programming language, sort of. It's a little hard to figure out, but what you do is you use your cursors and then you do some trial and error. Trial and try again, and just try something out, see what you get, try something out, see what you get until you work out how it works. All right, we're not doing a DC simulation, so this dot measure is not even done. But this dot measure, this is an AC simulation, which we've done. FT. FT is the symbol for the unity gain frequency, so it's kind of a natural variable name to use. When, so this is AC, remember my horizontal axis, my independent axis is frequency. So what is the frequency when the magnitude of the voltage at out equals 1? Remember, when we're doing an AC simulation, we get complex numbers. We get real part, imaginary part, or magnitude and phase. When we talk about unity gain, I mean a magnitude of 1. I don't care about the angle. So when we do decibels, it's 0 decibels, and a magnitude is the same thing as a magnitude of 1, whatever the phase is. Be careful. If you just say V out equals 1, according to the documentation in Spice and all the other spices really but in LTspice it's called out. This is the real part equals 1, unless you're talking about imaginary numbers. All right, so mag is the magnitude equals 1. You can also do ABS, I think. Maybe. Let's try it. Try it. Run. We get that. Where do those results for the dot measure results show up? If you know, it's under Spice error log. And here we go. Look. Hey, dot step. Here's our first step. This and this, and then this and this, and then this and this. Isn't this cool? Our measurement for step 1. What is step 1? Step 1 is this combination. All right, it doesn't list them out and whatever, but that's the information you want. ABS, V equals 1. Okay. Do you remember that we had 10 nanoamps or 10 microamps and 36 picofarads, or 360 picofarads. That was 3.6 times 10 to the minus 10. It was this one as our original parameter. So there'd be step 1, 2, 3, 4, 5. Step 5, we get an FT of 98.286 hertz, because my axis is in hertz. That's 100 kilohertz, or close enough. And we've kind of verified that we're doing our calculations right, that we found that. Always, 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 when you do a dot measure statement, always, did I say always? Always check numbers that you know first. Okay? And here we go. We got all our numbers. We did this. We're still at, we didn't change our default temperature, 27C. That's wonderful. Did all of our measurements for us. Hey, do you know there's other measurements, right? So we have, don't we need to measure the maximum gain? Dot mes AC we'll call this A0, which is the gain, right? And I think it's just find max of the absolute value of, what is it? V out. Count. Is that the right one? Run the simulation, Control L, and now we get dot mes. Here's FT. Didn't show up. Find. Run that. View our spice error log. Succeeded. Where are those results? Am I not doing this right? Clickable analysis. Okay. Find. Result name A0. Genre. Max. Alright, so we want max of, try that. You see how I'm doing this live? I'm doing this live because I don't remember everything, and videos that make it look like everybody remembers everything all the time really aren't being so, nice, honest, I guess. Maybe you do remember them all the time. I don't. I have better things to remember. Okay, so look at this. So we have a whole bunch of steps. Here's a measurement FT. Here's my measurement A0. It worked this time. Maximum. This is, because we have ABS, that's why this is always 0 degrees. Okay, we go from 0.1 to whatever. That's our whole interval. We can restrict that interval to look for, local maxima as we want. And we see that it's 105.9, 105.9, 105. It drops to 105.4, which is a half dB drop, which is just a small amount. And it's really like 105.5 or 106 dB for all of these steps. That should be a little surprising. Unless you know how this works. Unless you know what factors go into what sets the low frequency gain for this sort of two-stage amplifier. And in fact, that's a homework question for you to think about. You have all the information you need to do that. But this is just a way to do some measurements and do them all quickly, and then you get legit numbers. You don't have to worry about getting your cursor in the wrong place. Well, you know what? The final thing that we wanted to do, remember that we were looking at here, we found the 3 dB frequency. Well, isn't the 3 dB frequency the, like down here? Yeah, it's like 3 dB from the maximum. Well, you know what? We can say find this. We already have, whoops. We already have this. We already have this control enter dot measure. This is AC F3. And what is this? When? Isn't this a cross? Oh yeah. Oh yeah. Check this out. Well, what is 3 dB? 3 dB in voltage is 1 over the square root of 2, or 0.707. How about this? When ABS, a V out, okay, equals, oh, we're going to do math here. We're going to do some math here. What would it be? A0 times square root of 2. Actually, it'd be divided by 2. Even Professor White makes mistakes. Does this work? I don't know. Let's try it. Run the simulation. It's actually not necessary to run the simulation again if we're using the same data that's available. And there's other tricks, but we're not going to deal with those right now. We're going to view our SPICE error log, FT, A0. What is this? Absolute value of that. Okay, these numbers aren't. What is this? What? Hey, do you remember step 5? What was it, step 5? 1, 2, 3, 4, 5. This is our original simulation. That was 10 microamps and 360 picofarads. Okay, you got to get your scientific notation correct. Do you remember what the 3 dB frequency was? I do. It was 0.4 something hertz, right? Do you remember that? Well, I hope you do, because that's why we use the cursors. We do the cursors to cross-check our dot measure statements. Let's go down here. Step 5. What is the result of that measurement? 0.4. 0.4 hertz. This is awesome. All right, so I think we did this dot measure statement correctly to find our 3 dB frequency, because this one is okay. If now getting 1 point correct does not mean that you get the whole thing right, because if you think of two lines, any two lines that are not parallel in the same plane, of course, always cross at 1 point. So you could just be doing the completely wrong thing and going in the wrong direction, and you just found an intersection here. All right, so I'm pretty sure this is correct, because these numbers go in the trend that I expect, factors of 10 all over the place. Wasn't that cool? All right, so you're welcome to use cursors on here, and please do cursors as you've seen me do, but you don't want to do that all the time. It's better to then codify your measurements into dot measure statements. In this case, they're fairly universal, but if you're doing like logic delays and such, you have to count rises and falls and such. Those of you that are in the chip design class know that know about that. But dot measure is, well, excuse me, great for everything. All right, so we're at 23 minutes. It's time to shut down part 3, but we have walked through everything. If you're still hanging on from here, you are probably aware that I talked fast and I showed you a lot of things. So, I don't know. I'm not really going to apologize for a boring video. I do try to make them not a waste of your time. All right, so talk to you later. Ask me questions if you're my students. If you're not my student, come to Valparaiso University, and then you can be my student. Or just, yeah. Stay well.